So good morning, everybody. My name is Borek Pacak from Czech Technical University, and it's my pleasure to welcome you on the third MMP webinar entitled Perform a Platform Run. As this is a live webinar, please feel free to ask any questions during the webinar or during the dedicated discussion at the end. But if you are not willing to speak, please mute your microphone, as it can help to maintain a good sound quality to all. So let me first shortly introduce MMP project. The goal of MMP is to develop integrated modeling platform called MuPIF, targeted especially to multiscale and multiphysics problems and allowing to easily integrate existing legacy simulation tools and databases. There are altogether 8 partners from 5 different countries involved in MMP project with 2 industrial end users. You can see the partners logo in the bottom part. The integral part of the project are 2 case studies, one focused on modeling processes of photophore light conversion in light-emitting diodes, LIDs, and other on modeling copper, indium, gallium, selenide, CIGS, thin film processing for photovoltaic devices. MMP is a part of EU Multiscale Modelling Cluster and has been funded by EU under the 7th Framework Program. For more information about the project and its aims and activities, you can visit its website www.mmpproject.eu. Today's webinar is the last one in a series of 3 MMP webinars. The first one on generic platform design, where the platform design has been introduced. We have covered the object-oriented design of the platform, introduced the fundamental classes, and presented the platform main features. We have also explained the concept of distributed parallel model, allowing to take advantage of distributed and parallel computing. And finally, the platform installation has been covered as well, including demonstration using simple examples. The second webinar, entitled Build Your Own API, has been focused on the description of application programming interface, which defines the set of routines and protocols using which the platform interacts with external simulation tools and data repositories. The different approaches how to implement the application interface has been discussed and somehow presented on examples. Finally, the partners from MMP project have shared their approaches and experiences in connecting commercial and in-house developed simulation packages to the platform. In case you are interested, the recording of the webinars is publicly available from MMP web pages. Just follow the link to public events. In today's webinar, we will give a short overview of a platform design and features that will be demonstrated in following live demonstrations. As already mentioned, 2 sandbox scenarios are being developed in MMP project, one on CIGS processing and second on optothermal LID modeling. Both simulation scenarios will be introduced and demonstrated today in a live demonstration. Finally, a discussion session is scheduled at the end. Sorry. Okay. So let's start with a short overview of the platform design. The platform developed within the MMP project is called MuPIF. It's based on interacting distributed objects. We have chosen Python language thanks to its fast and efficient scripting capabilities and availability on virtually all platforms. The core of the platform is built on Python language, which is extended by introduction of new abstract high-level classes representing individual entities in our multiphysics and multiscale modeling space. These classes represent not only individual simulation tools, but also properties, spatial distributed quantities, solution steps, units, interpolation cells, etc. The platform defines abstract universal interfaces for all relevant classes, allowing to manipulate the individual instances using generic standardized interface. Such communication with individual objects naturally abstracts and hides all implementation details, including internal data and storage format used. The platform allows to define, let's say, complex workflows along the process chains and along all relevant scales, as shown on the figure on the right-hand side, in a plug-and-play fashion consisting of individual models. This plug-and-play architecture is facilitated by abstract class interfaces. The data exchange for a given model is shown on the bottom. This data exchange operating at selected resolution scale involves the initial conditions that come from previous processes. Inputs come from lower scale in terms of effective properties and in terms of boundary conditions from the upper scale. Similarly, the output represents boundary conditions to a subscale models and effective properties for the upper scale models. The data passed to, from, get-set methods are objects representing properties and spatial fields that come with their own interfaces. This allows to pass any object implementing a related interface. For example, this allows the platform to support multiple data formats, as these raw data can be encapsulated into the objects implementing the required interface, and is actually only the interface that should be used for communication with an object. So you can think as these green allows as the data being plugged into the workflow scenario, and these data can represent different data formats, data locations, etc. As will be demonstrated in the live demos, the platform supports distributed simulation scenarios, where individual simulation tools or data can be distributed across the network. This is facilitated by the concept of distributed objects, where communication with remote and local objects is fully transparent. The individual objects representing applications or data can be located on different computers, and the method invocation as well as parameter passing is done transparently and securely via the use of the proxies. The key feature is that the communication with the remote object is fully transparent to the user, which can develop its simulation workflow locally and then switch to distributed case without any changes. Today, we will have two live demonstrations, one on coupled optothermal simulation of LIDs and the second on CIGS formation modeling. The first demonstration will be presented by Mikko Majanen from VTT. I am now going to switch the presentation to him, so let me switch. Mikko. Okay, Mikko, the presentation is yours.
Okay, thanks, Borek. So, hello all. I'm Mikko Majanen from VTT, and I present the work package 2 case about coupled optothermal simulation of an LED. And our optical model consists of 2 models. The ME scattering model calculates the scattering probabilities and the scattering angles for the ray tracer, and then the ray tracer calculates the angle-dependent spectrum, meaning wavelength and intensities, and the thermal absorption of the lead phosphor material. These both models are implemented by VTT, And ME scattering model is implemented in Python language and ray tracer in C++. You can download the source codes of both models with their MuPIF application programming interfaces from GitHub. And you can see the link here below. And as I said, they are freely available there, and they are licensed under ABAS license version 2. The thermal model consists also of two models. A thermal resistance circuit, TRC model, takes care of computing the resulting effective thermal conductivity of one or two types of particles embedded in a given matrix. And then a continuum model of the LED package that includes also the heatsink, uses transient heat equations and adequate boundary conditions to provide the heat dissipation throughout the device. These submodels are written either in MATLAB or COMSOL, and the MuPIF API for these is used to interact with the MATLAB to prepare the data and to run the continuum model via COMSOL server. Okay, then let's take a look how these four models are coupled together to form an optothermal simulation chain. So first, all these four models need some input data from the user, because we have to specify all the materials and geometry and environmental and user conditions. Then the ME model is solved first. It calculates the phase functions and scattering cross-sections that are used as inputs into ray tracer. Ray tracer produces the thermal absorption field and the LED spectrum with wavelengths and intensities. And from the spectrum, we can calculate, for example, the color coordinates and color-correlated temperature CCT for the end user. From the absorption field, we get the heat generation due to the absorption, and this is passed to the heat transfer model as an input. The heat transfer model uses also the effective thermal conductivity as input, that is calculated by the thermal resistance circuit model. And finally, heat transfer model produces the temperature fields in steady state and transient, and so the end user knows both the optical and thermal behavior of the simulated LED. Here are some examples from our simulation script. It is a normal Python script, as you can see. In the script, we first set up the connections to the name server and the applications. Then initial fields are set from thermal application to the tracer application using get and set field methods. And then we are setting several properties to each application. For example, here we can see the host material refractive index that is set to the MuPIF. Then, for example, the particle number densities and volume fractions to the ray tracer here. And after the properties are set, then we can solve the applications. So each application is solved by using the solve step method. And after solve step, the results can be obtained by reading the properties or fields from the applications. So for example, here we have the CCD and the thermal field. This figure shows our simulation network topology. So here in the middle we have the name server, which is in a public network due to the security policy issues. Because this name server has to be reachable from application servers, and if it was inside the company networks, there could be firewalls and so on that prohibits the access to the name server. Okay, then the application servers. The thermal applications are run inside TNO network, and the optical models are run inside VTT's network. Then we initiate SSH tunnels from the application servers to the name server for the data transfer. And SSH tunnel is also initiated from the client to the name server. In our live demo today, this client is actually running on the same machine as the name server. But in principle, it could be anywhere. We have tested it, for example, so that it is in the CTU in the Czech Republic. Okay, to make the demonstration reasonably short, we use some optimizations. First, in the mesh scattering model, we can read the output data from its database, since we use the same parameters as in earlier ones. And in this way, we will save about 5 to 7 minutes. Ray tracer uses only 10,000 rays. This will save about 25 to 45 minutes compared to the 1 million rays. On the other hand, the results are not so reliable. And thermal model uses pre-computed results from an earlier run with the same parameters, and this will also save us about 9 minutes. So normally this simulation would take 40 to 60 minutes, but now we are doing it in about 2 minutes. Otherwise, the connection setup and data transfer between user and applications is as normally. We have only speeded up the solving phase of these applications. And let's then start the demonstration. Okay, so on the left, there is the ray tracer and the VS server. And on the right, we have the simulation end user. And first, we can check that all the applications and the name server are running. So we can see the name server, MMP application, ray tracer, and the thermal application. They are all up and running. And then we can start the simulation chain. Okay, as I said earlier, it first connects with the name server and applications, then it extracts the initial fields from the thermal app and sets them to ray tracer application. Then we are setting also other properties, and then we solve the MIA application. In the MIA server side, we can see that something happened here. It prints out the refractive indices of two phosphor particle types that we used in the simulation. And then we can see that the MIA application was solved. Then we set some properties again, and then we start solving the ray tracer. In the ray tracer side, we can see something happened here. These numbers are actually inputs from the MIA model. There are also the number of rays we use, particle number densities, and how many different particle types we have in the simulations. Okay, and the ray tracer was solved, and the thermal application field was transferred to the thermal application, and the thermal application was also already solved. And here we print out the temperature as a function of time in the center of the LED package. Okay, that was the end of our simulation. So as a result, user knows the optical and thermal behavior of the LED. And on the right, you can see examples of temperature and thermal absorption volume fields. And our next step in the project is to use this optothermal simulation chain to find the optimal phosphor particle mixture for a certain target CCT value. Okay, thank you for listening.
Thank you, Mikko, very much. I will switch presentation back to me. So the next presentation, the second live demo, will be on a CIGS processing, and this will be given by Ralph Afterfeld from Access. So now I am going to switch the role to Ralph. Okay, Ralph.
Okay, hello.
The presentation is yours.
So, hello, my name is Ralph Afterfeld. I'm from Access, and this presentation is mainly done by 3 persons here. It's Harman Rooms, who will start the presentation, and with Luke Thielen from Celsian, which provides us with a bunch of information. So let's start with Harman Rooms.
Okay, thank you, Ralph. So to give a small introduction to the problem that we're discussing is that, as you know, we work on different types of thin film solar cells. These thin film solar cells have some advantages over the normal crystalline silicon, and that is because it's much thinner, you can bend it. It's flexible. You can use it in different applications. And one of the type of solar cells we are working on is CIDS, thin film solar, where the absorbing material consists of copper, indium, gallium, selenide. The typical thickness for the absorber layer is 1 to 2 micrometer, and the CIDS is a crystalline material, which is normally of the chalcopyrite structure, but there are also other phases possible. Can you go to the next slide, please? The process that we are working on is the 2-stage process, where you start with a glass molybdenum substrate and a multi-layer precursor made of copper, mostly copper, gallium plus indium. This goes into a furnace with a selenium atmosphere, and in this furnace the precursor crystallizes into the copper, indium, gallium selenide phase. If you do the things right, if you get a bad process, you get a bad product. So if you look to the images in the real world, you have a precursor, you put it in the furnace, and you get a result. There's not a lot of exact knowledge about this process. There is a lot of research done, but it's quite difficult. There are a lot of knobs to turn, and this is costing time and money for each new process that you set up. So ideally, we would be able to predict this process, and therefore we wanted a model, so the digital world where you can simulate the processes in this oven, which is a large-scale oven with centimeter dimensions, heat and gas flows. And there's a microstructure evolution where the typical dimensions are very small, where kinetics and thermodynamics are there, and diffusion. So in the digital world, you also would ideally simulate a precursor, put it in the simulated furnace, and get the material out, in which you can optimize your process. This was it. Ralph, you can go ahead.
Okay. So yes, here's a more formal description what we want to do in the simulation chain. We want to describe in a digital way what's going on the process level with a macro simulation package, and what's going on the microstructure with a microstructure evolution simulation package. We couple these two scales with providing the data for setting up boundary conditions on the other levels, on the other scales. So it's a temperature profile which comes from the macro simulation, and that serves as a boundary condition for microstructure evolution. From the several statistics over several points in the macro field, there's an evaluation of microstructure done, and the concentrations or phase fractions are given back and are mapped from by experimental data tables back to a measurement of the emissivity, which serves as a boundary input back for the macro simulation level. Additionally, we evaluate the overall quality of the sixth component by calculating a quality factor of the statistics of the microstructure. And this is an additional value to judge the quality of the six components. There are two software packages which are involved are on the macro level. Xtreme, that's a modeling software developed by Salvi and Glass and Stoller from Eindhoven in the Netherlands, and it's capable of doing high heat temperature processes, flow processes, and a lot of others. I will not go into detail here. There are a bunch of applications for this software, and you can study the slides afterwards. It's just to give an impression what this software can do. On the microstructure level, the software MuPIF combines the phase field model with the diffusion solver and thermodynamic data, and that is done for simulating the evolution of the microstructure. There are also a bunch of applications major in simulating technical alloys, and that's only to give an overview of the software. What we do in the simulation chain, the MuPIF platform is here a typical distributed setup. So those software packages are running on server sides, one for Xtreme and one for Micros. One in Salvian in Netherlands, and one in Aachen in Germany. And for example, the client script can be run anywhere, for example, for end user evaluation at TNO somewhere else. I tried to visualize here a little bit the setup process. So we have a central name server where all the components of the framework have to register, and which provides handles for the client script for communication. So what's going on? The client script steers the simulation chain, contacts job managers for both external applications, and allocates job and gets back handle from certain interfaces which are steered from the job managers. So I want to present a little live demo here. So we're running the simulation chain and how to monitor the results. In principle, that's the view of the end user. At the end user side, a bunch of scripts have to be installed and which will be run. So we see one simulation script, and we can run them. I recommend to run them on the console, because you see every output here, and the output doesn't vanish. So let's start them. What you see here is the grid setup. So we want to have one Xtreme interface and 4 Micros interfaces. So we set up communication tunnels. These are the windows you see here. And we have now available for the simulation chain one Xtreme interface involve microinterfaces. Now I just display a little performance table. The simulation is done all here at Access, so it's local communication, and it's very fast on the microstructure because it's just collecting pre-calculated data. And on the macro level, that's live, so it's a very coarse grid on the macro level, and the extreme is really running fast on this coarse grid. So the simulation is going on, and what the end user can do with the script, collect some monitoring data here. I've written a little NuPIF script to show this. And here you can see what's going on. In the plots here, I listed all the interesting factors for coupling. So it's a selenium concentration here, and it's rising. And the macro temperature profile here. So that's a direct link here via emissivity. And all the relevant microstructure statistics which I use to evaluate quality factors. So some fraction of phases and 6-layer thickness, slightly evolves here, getting bigger. And that's what the end user can do while the simulation is running, or just viewing with power view some output from the simulation. And the typical results are like raw data from the simulation. So all the simulation data from the external applications are available. For example, the microscale temperature distribution in 3D from Xtreme, or the microphase evolution. So I made a little video here of how it looks like. And what you see here is the 6-layer, and here I make the gas phase transparent to see the surface of the 6-layer. And you can get these overall statistics with the quality factor, which are done from several points of the microstructure of the surface, and these statistics are collected, and then you can get an overall quality factor for the 6 components. So future work is to validate and calibrate this models which are participating, and to fit it to experiment and to make predictions out of it. So that's all from me. And now we can go on with the discussion.
Okay, thank you very much, Ralph. So I'm going to switch to my screen. So as Ralph has indicated, now we are coming to the last point of today's agenda, which is the discussion. So if you have any question or comment, please don't hesitate and ask. Okay, if this is not the case, let me finally thank to all of you for joining us and participating. And in case you are interested, the webinar has been recorded, and the recording will be available soon on MMP website. So thank you again for joining us, and have a good day. Bye-bye.